Welcome to the lecture 3 of statistical mechanics. In today's lecture, we will calculate the probability density for a microcanonical ensemble. So let's start. Let rho PQ be the probability density for a microcanonical ensemble. So a microcanonical ensemble is specified by specifying the number of particles, the volume V, and the energy E. So it's a constant number of particles, a specified volume, and a constant energy E of the system. Now, for this density function to be a probability density, it must be normalized. So the integral over rho PQ d3n P d3n Q must be 1, where the PQ values cannot be taken arbitrarily, but it must satisfy that the Hamiltonian of the system must always have the value E, where E is the energy of the system. Now, I have also stated a equal probability hypothesis that says that every accessible microstate must be equally probable. So the rho PQ must be a constant probability density, so that every microstate that is realized by the system is equally likely. So we assume that the rho PQ must be a constant. So let's just put the C in here. We get, we can take the C out of the integral. So this is C times d3n P d3n Q must be 1. So the C just comes out to be a phase space volume. So 1 over integral of d3n P d3n Q. So here the constraint is similar. So here we have HPQ must equals E. Okay, so I can now write the probability density So our microcanonical probability density is RMC is equals to a constant, which is integral d3np d3nq, where the Hamiltonian can only take the value where the total system has the energy E, and if QP is accessible, the phase space point is accessible, then it will have this probability, which is a constant, otherwise it is 0. If QP is not accessible, now we usually write this integral as omega, which is the number of microstate that the system has. Now we will apply the Boltzmann hypothesis to calculate the entropy of an ideal gas. So let's take the ideal gas. We will again take the microcanonical ensemble, so it will have an n number of particles with a volume constant volume V and a constant energy E. So the Hamiltonian of the system, rho PQ, is equals to a constant, which is equals to the sum of kinetic energies of all the particles. So this is P sub I goes from 1 to 3m, plus it does not have an interaction because it's an ideal gas, so interaction energy is 0. So I can write this as Pi squared, so that's a square. I goes from 1 to 3n is equals to 2m E. Now I stated that the entropy is equals to Kb times natural log of number of microstates. Now we will calculate the omega. Omega is equals to integral that was d3n p, d3n q, and not every pq value, but all those values where the Hamiltonian has the energy E. Now we can separate those out. So this is d3n p integral d3n q. Now this is just the volume V of the system raised to power n, because there are n number of particles, and here the constraint is similar as pq is E. Now we will calculate this integral in the momentum space. Now this constraint can be equally replaced by this constraint, so let's just calculate this integral. So this is d3np and sigma pi squared, I goes from 1 to 3n, is equals to 2me, is equals to, now let's see, this is a surface area of a sphere with a radius 2me square root. So the radius of the sphere is r is 2me. You can see that this is if you take the 3 dimension, this is just like x squared plus y squared plus z squared is equals to 2me square root of it and then square. So if you compare this one with this constraint, let's see that this is a surface area of a sphere in 3n dimensions. Now what is the surface area of sphere in, say, 3 dimensions? It is 4 pi r squared. So you can write this as 4 pi r to the 3 minus 1. So this is a constant that depends upon the geometry, that means the dimension that you're talking about, a sphere in 3 dimension or a circle in 2 dimension, because in 2 dimensions it becomes a 2 pi r. So this factor depends upon this dimension that you're talking about. So it depends on the geometry, and r to the 3 raised to power r raised to power 3 minus 1. Here 3 is the dimension of space. So a similar argument can be given to this equation. Now we write here as geometric constant Bn and r raised to power 3n minus 1. Okay, 3n is the dimension of the sphere. The sphere is in 3 dimensions. So you can just put it here. So this is Bn r raised to power 3n minus 1 v to the n. So this is omega comes out to be this. Now we know the radius is this, and I also make an approximation that n is very, very, very larger than 1. So because there are lots of number of molecules, n is the order of 10 to the 23, so we can make this approximation and just remove this one. So our number of microstates comes out to be omega is equals to Bn times, what is r? This is 2me, that's a square root, so this is 3n over half and v to the n. So this is the number of microstates that our system possesses. So let's write this down. So omega comes out to be a function of the energy of the system and the volume V. So omega as a function of E and V is equals to Bn, a constant that depends on the geometry, and 2me raised to power 3n over half, and the volume V raised to power n. So let's calculate the entropy Now, since the omega is a function of energy and the volume, the entropy will also come out to be a function of energy and volume. So S as a function of energy and volume is equals to the Boltzmann constant, natural log of this omega Bn to me raised to power 3 over n over half raised to power n. So this is equals to kb natural log of Bn, and so this is plus n will come out, so this is kb n log of 2me raised to power 3 half and v. So that's the entropy as a function of energy and volume. So we see that the Boltzmann equation serves as a bridge between the thermodynamics and the statistical mechanics. So this is the statistical part that I have calculated from the phase space, and S is a thermodynamic variable. So this equation lists the statistical mechanics with the thermodynamics. Now, since now we know the entropy, we can calculate all the relevant thermodynamic variables like temperature, pressure. So let's do this. So you know that the temperature is equals to ds du. So U is energy, so this is ds dE with a constant volume. So you can calculate this. So this is, since this is a constant, it is 0 and kb n, and this is with respect to E, so this is 2m E 3 half V, and derivative of this, so this is V, and this is 3 half comes out, so 2m 3 half, and this is 3 half, and 3 half minus 1, so this is 1 half. So you can write this as, you cancel this factor, so this factor goes, and we get the temperature. So I just write the last equation. E here is 3 half kBT. So you see that the internal energy of an ideal gas only depends on the temperature that we know earlier, so we have derived this by the statistical mechanics. Now, the last thermodynamic variable that we will calculate is pressure. So pressure is given by, now let's calculate the pressure using that equation. So let's now differentiate this equation with respect to V, holding the entropy constant. So 0, because the entropy is constant, and that's just a constant, so again a 0. And now this is n. So let's write this equation a little bit easier. So this is kb log Bn plus nkb, so 3 half comes out, so this is 3 half log 2me plus nkb log v. So now let's differentiate it. So that's a 0, and this is 3 and kb by 2. Now differentiate this, there will be 2me, and this is 2m, and this is dE dV at constant entropy plus nkb over v. Now let's rearrange this. So if I put the value of the dV at constant entropy, so I get 2m cancels and nkb also cancels, so this is 3 half, this is 0, 3 half, and I get a minus p, over the energy minus 3/2, that's a P, that's the energy, and plus N over also and also gets cancelled. So this is 1 over V. So that becomes, so this is P 3/2 E is equals to 1 over V. Now so this is PV is equals to 2E over 3. So that's our equation of state for the ideal gas. Now we have calculated the value of energy in terms of temperature. It is N by 2 kBT. So I'm sorry about that I have just written the formula for this without drawing this. There's an N here. Okay, please correct that. So this is 2 by 3. Oh, sorry, there's a 3 also. 2 by 3 and 3/2 N kBT. So that becomes PV is equals to N kBT. So that's our similar equation of state for an ideal gas. We have derived this using the statistical mechanics. And that's it for today, and thanks for watching this video.